All right, today's video lecture is on concentrations of solution or solution concentration. There are many different types of ways of describing the concentration of a solution. And when I say concentration, what I'm looking at is how much solute is dispersed through a given amount of solvent. Okay, so how many particles of solute are there per sample of solution? Okay, and if we're comparing equal amounts of solution samples, the one that's more concentrated will have more solute in that sample. Okay, so the more concentrated something is, the more solute there is per unit of volume. The more dilute it is, dilute means there's a less set of concentrated solute particles per given amount of volume. Okay, so words like dilute, concentrated. An application of this obviously is when you go in the store, you buy orange juice, frozen concentrated orange juice. You dilute it with water to lower its concentration to make it more palatable. Why would we want to sell or purchase or buy things in concentrated form? It saves money. It's cheaper for the plant because they don't have to ship so much material, which a lot of it's just water. We can ship the concentrate form. We can add water once you get it to your house. Water is readily available here, and therefore it'll save you money and also the supplier money too in transportation costs. So it's a win-win. So that's why a lot of times, even myself, I buy concentrated stock solutions from my chemical supplier. Therefore, all I have to do is add water to whatever concentration I need for in a specific experiment. Okay? Now, here up above is an example of two beakers of two different solutions, solution A and solution B. And both of them are solutions. And again, you can't tell it's a solution because of the fact there's a single phase. You don't see multiple things there. I took a small sample size, as indicated by the circle. So that is the sample size taken out of solution A, and let's assume it's the same size as B. And then I've blown it up so that way you can see the dots. The dots symbolize the number of solute particles. Based on this information or this pictorial example, what can you conclude? Hopefully, what some of you said is that solution A is more concentrated than solution B. Because there's more solute particles in that given amount of volume, A is a higher concentration than B. Okay. Now, when it comes to concentration, for those of you taking AP chemistry, the only concentration that we specifically deal with almost all the time is molarity. Molarity of all these concepts is probably the most important for you to get down while you're at home in this quarantine. It's the most important concept. And we can show quarantine, my bad. We can show concentration in molarity by putting brackets around something. So if you ever see brackets around a chemical formula like this would be an example of they're asking for what is the concentration of HCl. Okay, so let's assume both solution A and solution B are HCl solutions. Brackets around something is explicitly telling you what is its concentration in molarity. What is its molar concentration? And to get molar concentration, the equation is given off to the right. Now on your chem helper, all of these equations are on your chem helper. So if you look at your blue chem helper and find the section of it that says solution, the column that says solution, you should see all 5 of these equations put together. Actually, the top 2, I should say 4. The top 2 are put together in the fact that I've said grams or milliliters over grams or milliliters. Okay, which I'll get to in a second. So these two I've kind of put together because it's really the same concept, but there are 4 different types of ways we can look at concentration, and they're on the chem helper. All you've got to do is be able to do exactly what it tells and then plug and chug and do the math. So for molarity, it's how many moles of solute are there in every liter of solution. So if the circle that I put here was an example of 1 liter of that solution, let's say it's a really big beaker, this too is a 1 liter sample size. How many moles of HCl are there in every given 1 liter of that solution? Okay. If I take another sample somewhere else in the same solution, how will that concentration compare to the other concentration in solution B? Okay. Now again, I didn't make the circles very good. These should be about the same size, but you'll notice this has 1, 2, 3, 4, 5, 6. There's 7 particulates in this picture. If I were to take the same sample size from the same material, you would have the same number of solute molecules. So that concentration is evenly distributed. So no matter where you take the sample from it, it should be exactly the same because they intermingle with intermolecular forces and equally disperse throughout the solution. Okay? So brackets around something is molarity. So if you see brackets around HCl, and they say 1.5 big M, what that means is the concentration of this HCl solution is 1.5 molar. What does that mean? That means there's 1.5 moles of HCl per every 1 liter of that solution. And again, when I use the word solution, I mean both parts. That includes both the solute and the solvent together, the solution. So in 1 liter of that material, if I were to pour it out, I would find, if I had an electron microscope, I would find that there would be 1.5 moles of HCl particles in that 1 liter of solution. Okay? So brackets indicates molarity. So all we have to do is be able to convert, if we know the grams or number of particles or the volume of gas, we should be able now, based on the previous units, convert it into moles and simply divide that by the liters of the solution and you get your molarity. Percent by mass and percent by volume. Percent by mass is often used with dry goods. Okay, so when you're looking at the back of a package and it says percent of this, percent of that, that's usually percent by mass. And we've done this throughout the whole year. Percent by mass is the mass of the solute divided by the mass of the solution or the mixture. Okay, mass of the part over the mass of the whole times 100 mass percent. If it's a liquid, you might do a percent by volume. Okay, maybe it's like a grape juice and they give you the volume of concentrate. They'll tell you the volume of the solute over the volume of the solution times 100. Percent by volume. Okay, application of this would be like usually alcohol's one that's probably the most common. And in fact, if it says 3.5% alcohol, it's 3.5% ethanol in water. So there's 3.5 milliliters of pure ethanol for every liter of solution. Okay, that'd be a percent by volume. So usually thinking of liquids. The other two types of concentration problems is molality. Molality used to be on the national exam, it no longer is. I still talk about it because of the application of things called colligative properties. But for the sake of this unit, you are, we're going to do some practice and homework, this will not be included on this year's test. Okay, we're going to focus mainly on molarity. There's a very small difference there. You'll notice with molarity, it's moles of solute. For molality, moles of solute, it's the same. It's the bottom that's different. Actually, molality is the only one that has the value being solvent. Only the solvent, not the entire solution. So it's moles of solute divided by kilograms, the mass of the solvent in kilograms. And that gives you molality. Mole fraction is exactly what it says. Put the moles of one of the particles, okay? If you have a mixture of things, how many moles of A is there over the total moles of all the materials? So moles of the part over the total number of moles of all the substances. That gives us mole fraction, okay? Now, the units. For percent by mass, percent by volume, the units is going to simply be a percentage. For molarity, it's capital M. Capital N stands for molar, which is moles over liters. Okay? Little cursive m is molality or molal. That is moles over kilograms. So if you see little m after something in the homework, that'll be molal. Big M, capital M is molar. And mole fraction has no units. It is simply a decimal value. So for example, if you have a mole fraction, that's 0.33. What does that tell you? That means 1 out of every 3 particles in the mixture is of particle A. So if you were asked to draw a particular example, if you had 12 particles, you'd have to make sure that 4 of them would be particle A. 1 out of every 3. So the mole fraction gives you the decimal, in essence, percent of one particle compared to all the other particles. Okay? All right. Let's look at some examples. Now, if you want to pause the lecture and try to do problem 1, 2, and 3, please go ahead and then start the lecture back up again so that you can see if your answers are correct. Okay? Otherwise, I'll go through these. Okay, the first problem. In order to maintain a sodium chloride concentration of ocean water for an aquarium, you must need 3.6 grams of NaCl per 100 grams of water. What is the percent by mass of sodium chloride? This problem, while it's extremely simple, students always make the same mistake. And for those of you that have paused the lecture and tried to do this problem on your own, you might have made the same mistake. The key thing with percent by mass and percent by volume is it says solution, not solvent. Water is the solvent. Sodium chloride is the solute. Solution is the two together. So the total mass of the solution is not 100 grams, it's 103.6 grams because you're mixing 3.6 grams for every 100 grams. Multiplying by 100 converts it into a percentage, and you should have gotten 3.47% sodium chloride. So 3.47% of the mass of that solution is sodium chloride mass. Now, if you wouldn't have put 100.3 in the bottom, put 100, then you added 3.6. It's not off by much, but on the test, I'd make this spread in these two numbers be a lot greater so that if you did not do that, you would get it wrong. Okay? All right, next one. Calculate the molarity. Key thing, identify what concentration units you're working with. We are now working with molarity. Calculate the molarity of 20 grams of sodium hydroxide dissolved in 200 milliliters of solution. All right. Molarity requires moles over liters. All right, so the first thing we've got to do is convert grams of sodium hydroxide, which is the solute, convert that into moles. So you need to know the molar mass of sodium hydroxide, which, believe it or not, is exactly 40. So we get exactly 1/2 of a mole. We'll divide the number of moles of solute by the volume of solution. Now, they use the keyword solution, so I don't have to do anything else to it, but you'll notice the problem here is the milliliters. Okay, molarity requires liters, not milliliters. So we have to make sure to convert. So that's a key thing. Make sure your units match. That's where I'm going to get the good old gotcha. Make sure the units match. So to convert milliliters to liters, we have to know the ratio, and that is that for every 1 liter, there are 1,000 milliliters. So in order to convert milliliters to liters, you need to divide by 1,000. So 200 milliliters is 0.2 liters. So 0.5 moles divided by 0.2 liters will give us the right units, and that gives us our answer, which is 2.5 big M sodium hydroxide. As a chemist, how would I read that? I would say 2.5 molar sodium hydroxide. The concentration, every liter of this solution, if I poured it out, would contain 2.5 moles of sodium hydroxide per liter of solution. Okay? 2.5 molar sodium hydroxide. So you might see in brackets, if I were to have this solution in a beaker, I would put NaOH in brackets. Brackets means molarity. And I would put down 2.5 molar. So that tells you that that solution in that container is 2.5 molar sodium hydroxide. All right, next problem, molality. Okay, so molality is a little different. Now we're going to do moles of solute over kilograms of solvent. Now, this problem's a little bit weird. When you collect maple sap, it usually takes about 40 gallons of sap to be reduced down. You have to boil off the water to get it concentrated enough to make it into maple syrup. So what's weird about it is initially the sugar, the sucrose in the sap is at a very low concentration. But in essence, you boil away so much of the water that when we get to the maple syrup itself, that actually the sugar is got a greater amount of it mass-wise compared to the water. However, we still keep the water, in this case, the solvent, because that's what it started off before. So this kind of a tricky problem, I would never have this on the test anyway. But it is kind of a good practical application because we're in the springtime, and even now, because it has stayed fairly cold this spring, there are still people collecting sap still today. It's been going on for almost a couple of months. All right, so first step again, 67 grams is the sucrose. So again, we have to convert the grams into moles. Sucrose has got a very large molar mass. It's a huge molecule, which is, I added up previously, 342.34 grams per mole. So 67 divided by that gives us 0.196 moles of sucrose or sugar. And we'll divide that by the mass in kilograms. 33 grams. To convert that into kilograms, again, kilo, just like milli, stands for 1,000. So again, to convert grams to kilograms is the same as milliliters to liters. We divide by 1,000. So 0.196 moles divided by 0.033 kilograms gives us 5.93 molal. Okay, sucrose. So 5.93 molal sucrose is how we would say it. If you would just put the units, it would be 5.93 little m. Little m means molal, big M means molar. Okay? All right, let's turn to one other application of this is how do we prepare solutions in chemistry class? Especially those taking AP Chemistry next year, you're going to be asked to make solutions and be aware of how to do that also for the test. Now, those of you who haven't, obviously this is something that probably you won't have to be worried about too much because, again, we really can't do labs anymore. So usually labs I would normally have you do, but if you make the solutions to practice this, we're not going to be able to do that now. But it's still good information for you to be aware of. If you are making a solution from a dry material, okay, and typically, again, we're going to be asked to make a molar solution of it. I want to make a molarity of a specific concentration. What I have to do is go in my back of my storage room and find the bottle, the dry bottle of sodium hydroxide. Okay. Inside that would be pure sodium hydroxide. To make a 2 molar solution, the first thing we would have to do is figure out, okay, we can't really measure moles, okay, per se. What we'd have to do is figure out the grams. So we have to figure out what mass of sodium hydroxide would afford the appropriate number of moles to make it into that solution. So the first step is to actually use a calculator and figure out how many grams of the solute I need to measure out. Once I do the math and figure that out, I then can go ahead and use a balance to measure out that amount of solute. I'm going to then add that into what is called a volumetric flask. A volumetric flask has got a big bulb at the bottom where most of the volume occurs. It's got a skinny little neck. The purpose of that skinny neck is to make that one line be a very precise measurement of volume. So if I'm making a 1 liter solution, I would want to grab a 1 liter volumetric flask. And that mark on that neck would be 1 liter to an extremely precise amount. So I would grab the appropriate size flask for how much solution I want to make. I've measured out my solid, so I then pour the solid into the volumetric flask. I would then add whatever the solvent is. Most often it's water. I'd add water to it. Now I wouldn't fill it full initially. I'd fill it partially full, and then I would swirl it to dissolve it. I'd want to dissolve it first. Once it's fully dissolved, then I would fill it all the way rest to the top to the mark. And that mark then means I've got the appropriate volume. It's been fully dissolved. I would cap it. I would then shake it up to make sure it's evenly mixed, and now I've made my proper solution. So let's say you're a chemist in problem here. How many grams of sucrose would I need to prepare a 1 liter 1.5 molar solution? Well, if I look at the molarity equation, the molar equation is very similar to the density equation. It has, just like density equals mass over volume, molarity equals moles over liters. Well, in this problem, I know the volume and I know the molarity. So I plug it and chug it into the equation. 1.5 molar equals 1 liter over X. Okay, what I don't know in the molarity equation is the number of moles of sucrose I need to make that appropriate solution. So whenever we make a solution from a dry stock, the first thing you'll need to do is actually multiply molarity times the volume in liters. Multiplying the molarity times the volume in liters gives us the moles of the solute that you need to make the solution. So for this problem, 1.5 molar times 1 liter gives us 1.5 moles. So I would need 1.5 moles of sucrose to add to water to make it this appropriate concentration. Now again, we don't have mole scales, we have balance scales. So the next step is I would have to take that mole quantity and multiply by the molar mass, which for sucrose is 342.34 grams per mole. So if we then punch on a calculator, we would get 486.51 grams. So I would have to measure up 486.51 grams of sucrose on the balance. I would need to grab a 1 liter volumetric flask. I'd pour the sucrose into the flask. I would add some water, swirl it till it's dissolved, and I would add water all the way up to the mark, cap it, swirl it to shake it, to agitate it, to evenly mix it, and now I've made the appropriate liquid aqueous solution to do whatever experiment I want to do. This is the procedure we use for all making of solutions, and I've been doing it for over 20 years. So this is how I make solutions still today as I did 20 years ago. Find out how much solid we need, mass it, put it in the appropriate flask, add the appropriate solvent, dissolve it, and then fill it to the mark. The other way we can make solutions is by diluting them. As I've said before, I always buy solutions of a higher concentration. Sometimes, most often, you can buy these solutes as dry stock, but sometimes you don't. The only way you can buy them is in solution form already, like HCl, because otherwise you'd have to purchase as a gas, and that would have some very hazardous issues in transporting it. So things like that, we would actually, I would buy things in a very high concentration, because then I can make whatever concentration I need to use. Now we're going to use the mathematical formula, which is the molarity equation here, which is called, actually on your Blue Chem Helper, it's called the dilution equation. M1V1 equals M2V2. Molarity times volume equals molarity times by volume. On one side, we can have the stock solution, which is the more concentrated side. On the other side is the more dilute one that we're trying to make. Okay. Now, how does this work? This works because molarity times volume gives us moles. So when I add water, my volume is going up, but adding more water makes the molarity go down. So what's happening here is it's an indirect relationship. And just like Boyle's law, as you add more water, the concentration of it becomes more dilute. Or as you increase the volume of a gas, its pressure decreases. So whenever we have an inverse relationship, we get an equation. It's not a proportion. The most common mistake that students do on the dilution equation is they treat it like a proportion. That is not correct. Think about it logically. If I add more water, it can't make the molarity more concentrated. It makes no sense. So you got to think about logically. So the dilution equation is the molarity times volume of the stock side equals the molarity times the volume of the diluted side. Therefore, both sides, we have the same number of moles. I just have a bigger volume of a less concentrated side or a smaller volume of a more concentrated side. In both sides, they equal the same number of moles of material. So to do this, I would have to figure out what volume of stock concentrated I would need. I would then pour that into a graduated cylinder to measure out the appropriate volume of concentrated solution. I would then add that to my appropriate volumetric flask, and then I would simply just add water to the mark. Cap it, shake it to mix, and I've now diluted it down to the appropriate concentration. Okay, so let's do the last problem for today. What volume in milliliters of a 2 molar calcium chloride stock solution would you use to make 0.5 liters of a 0.35 molar calcium chloride solution? The word of in any algebraic equation means multiply. Those two numbers we want to multiply together. So 2 molar, we don't know the volume of it. So again, the stock side is the molarity times the volume. Only one of these variables we will not know. And the other side, the more diluted side, will be 0.5 liters times 0.3 molar. Now the great thing about the dilution equation is if the volume was not in liters, if it was in milliliters, we could keep it in milliliters. If we have milliliters on the right, we'll just get a volume of milliliters on the left. We don't have to have it be liters on both sides. Okay? But just make sure whatever units are on the right is the same units on the left. So now we just got to divide by 2 molar. We'll notice that the molars cancel, and we're going to be left with a volume in liters. So when we do the math, we end up getting a value of 0.075. Now, what's the units on the volume going to be? Liters. Is that what we want? No, the question asked for the answer in milliliters. So again, this is a place where on the test I could gotcha, because you would stop here and answer the answer with 0.075. But that's not the volume in milliliters. So every 1 liter contains 1,000 milliliters. So we would get the answer of 75 milliliters. So what I would do is measure out 75 milliliters of the stock solution, pour that into the appropriate volumetric flask. In this case, it would be a 500 milliliter or a half of a liter volumetric flask. I would pour that 75 mils in. I would add enough water to get it to the mark of being 500 milliliters or 0.5 liters. Cap it, shake it up, and we've made our solution. So this is how we make solutions from dry stock and also from more concentrated solutions down to lower concentration. Okay, so now the homework is going to be the next page. I think I've got like 12 to 15 problems. Each problem, identify, is it a molarity problem? Is it a molality problem? Is it a dilution problem? Go back to the appropriate equation to use, plug in your numbers, make sure you have proper units, and solve. And again, check your answer key. If you have any questions, again, reminders on Thursday at 1 o'clock, I will have a question and answer session on Microsoft Teams. So if you want to have questions on any problems you're having so far in the solution unit, just give me, just chime into that lecture and send me some questions, and I'll be glad to answer them for you. Have a great day.